Hello, welcome everybody. I'm Michael Hall. I'm filling in for Robert Wolf today, and you're watching the ARM Innovation Coffee. Every week we do a deep dive into the ARM developer ecosystem. Every live broadcast that we do starts with updates from ARM developers in and around the ARM ecosystem, followed by in-depth conversations with ARM experts or partners, anybody building something really cool that's going on. Each of our broadcasts has a Q&A, so if you're watching this on YouTube, you can ask us questions there, and we will bring those up to our guests or to ourselves and answer those live for you here on the air. And as always, if you enjoy this broadcast, don't forget to smash that like button and subscribe to the ARM Software Developers YouTube channel so you get updates from us here about Innovation Coffee and all of the other ARM broadcasts that we have going on. Today, like I said, I am filling in for Robert Wolf. He is on his way to our Cambridge office right now. In fact, he might be there by now, celebrating 1 year of the ARM developer program. So DevHub Live is going on there right now. You can see the link here to that event. If you are in Cambridge and you want to go to that, it is free to attend. If you have not already registered, you can register there. Hopefully there's still some tickets available. And we will be hearing from Robert in our Discord as that event progresses. So keep an eye out. He should be setting up a new channel there, sharing some pictures. I know we've got a bunch of ARM experts and ambassadors who are going to be there with him. Unfortunately, Gabe and myself are not attending that, but we are running Innovation Coffee here for you today. We have some really great guests for you today. A really cool startup that I just recently found out about was introduced by a colleague here at ARM. Called American Chip, and they're doing some really interesting work using machine learning to optimize software code for running on ARM chips. So without further ado, we will go ahead and bring them in. So I'd like to welcome Micaela and Guna, who are the co-founders of American Chip, and Raul, who is the lead compiler engineer. Is that right?
Yep.
All right, well, welcome everybody. So Micaela, why don't we start with you and we'll just do a round of introductions. Tell us about yourself and your background.
Yeah. Hi, Michael. Thank you for having us. Yeah, so I'm Micaela. I actually used to work at AWS and Microsoft and big user of ARM. And this is how the actual startup came about around optimizing code for customers running on ARM. So I'm the CEO and the co-founder. Nice to meet you.
Nice to meet you. And so what is your background? What did you do at AWS and before that?
Yeah, I can share a bit more. So I used to be in the professional services side and back in Microsoft and in AWS. And customers would come in all the time asking, hey, I'm running on Graviton, but this library that is really important for us may not be working as we want. And, I need somebody that really knows the low level detailed stuff. And that will require us to set up a whole team. So that made me think, hey, there should be some way to scale. How would a smaller customer do this, or a medium size, or even a startup? So this is how decided to put together some great people I have known across the industry and build up the startup with people from all over, from Barcelona Supercomputer or Guna from Intel. So it's kind of putting all the brains together at work for customers.
All right, well, that's a great way to segue into introducing Guna. So go ahead and introduce yourself. Tell us about your background.
Hey, Michael. Yeah. So I'm Guna. I have about 17 years experience in the industry, mainly on the verification and validation roles. I have worked with Intel, ARM in the past, in fact, and also IBM. I'm currently the co-founder here and also overseeing the delivery of the product at American Chip.
All right. And Raul, now it's your turn.
Hi, I'm Raul Torres. I did my PhD in Germany, specialized in compiler technology. And then thanks to that knowledge, I was able to work in the Barcelona Supercomputing Center, where I was investigating or researching in terms of extending the OpenMP parallel programming language for supporting multi-GPU uploading. And I think this kind of knowledge is very valuable for American Chip to the things that we want to bring to the ARM community and ARM developers community especially.
All right. Now, before we dive right into what you're building and what it does, I wanted to just ask you, what made you decide to strike out on your own and start this as a business? Micaela, you said you saw the need for it, but what made you decide that this was something that should be its own business and that you wanted to take the lead on that?
It's a great question. So there was technology to be built. So what we're hey, is everybody gonna go and inspect code and spend that time, or like how is this gonna scale? So my thinking was ARM today is gonna keep increasing its market share, and like the knowledge required to find these optimizations is very specific, and it ends up being with the person that actually did that optimization. It doesn't spread around unless you kind of go to that repo and do that due diligence. So by building a technology that we can generalize this stuff, it made sense to me, like it will help ARM also in growing, right? I did a couple of projects when we find really good stuff, and then it became maybe a Reddit conversation, and it ended up there. So how is somebody that is just starting gonna take advantage of that? So that made me think, hey, this is a good opportunity to find, as ARM makes its segue in the world, there's going to be a lot of good stuff to uncover and share across the industry.
And I understand we have some demos that you wanted to show today of, was Heiko? Is that how you pronounce it?
Yeah, Heiko. Yeah, maybe Guna, do you want to share?
Yeah, well, before we go right into the demo, can you tell us, what Heiko is? First of all, what does the name stand for? And second of all, what does it do?
Yeah, so actually we have like a set of slides that we want to run through. Maybe we can get started with that and then go into the demo automatically through the slides. Maybe that's a...
Sure.
Yeah, I think to answer the question, HACO stands for Hardware Aware Code Optimization. And what it does is, hey, like based on the hardware that the customer is running, like Graviton, Ampere, whatever that is, like there are optimizations that are precise for that hardware. So we build this technology that kind of identifies the hardware and can run, code optimizations through that.
All right. Well, that sounds like a good way to segue into the slides. So which one of you is going to share that?
I'll be presenting some just to ground the audience. Cool. So let me share my screen. Awesome. So just to kick it off, I mean, why are we doing this? I think it's a good place to start. And Mike, you were making reference to this, right? So we've heard from customers say, hey, I need my code to start leveraging, intrinsics, or I need this library doesn't scale really well in ARM. Like, let's say after 8 vCPUs, we're having some issue. Or, hey, like my team doesn't really know assembly, to be able to write this specific routine. So all this came together into, hey, we need something that can scale, that is, not expensive, and that can work across the board. And all the learnings that we have or that customers have, we can feed it back into a tool rather than like individual blogs that may, suggest this information. So with that, we built this kind of leverages a bit about why are we doing this, right? But there's ever evolving optimizations coming. Like there's actually a really good post that just came 2 days ago around how AI is applying some of these optimizations, and we'll go through those. So how can we keep nurturing this into kind of a database or generalization approach? And this is what HACO tackles. So the quick questions we're solving, and I think this is like a really good way to anchor the audience, is how can I optimize libraries without spending a lot of time? And, in some cases, HACO does give better optimizations than humans, and in others, it does not. It gives it as the same, but you're not spending the hours just going through that library or that application. So this comes to the second question around how can I ensure, that I'm running the most optimized version of my code with a tool or with something I can continuously run or run every launch that happens, and keep building over that without having to spend time analyzing or reading some 100 blogs to find this out. So Guna, maybe you want to talk about how it works?
Yes. So this slide goes over the engagement model that we currently have. So broadly, there are two major engagement models that we currently have. One is the professional services aspect, where we will work closely with the customer and migrate or port an application from x86 to ARM. The other engagement model we currently have is we have a Hacko Assistant available. The prototype version is available now, which basically is a compiler front end. We can use this to either do a hotspot analysis, or we can, have if you have a closed source scenario where the customer is not willing to share the code. So in those scenarios, we can run this assistant locally on the customer's machines and collect the data from the machines and give back some feedback on what are the recommendations or what are the potential places for performance improvement. Along with this, we also have a developer studio, which throws up like a input box, which the customer or any developer can input some piece of code, select what optimizations he wants, and then automatically it transforms the code which is in the input box into the optimized version in the output box. So we have these engagement models which are available at this point. But I think the key takeaway is we are still in the prototype and the beta phase. We do have a roadmap to add in a lot of features, and the box on the right actually goes over some of our key expertise we have. Like all of this, if you look at it, is focused only on ARM architecture at this point, right? Yeah. So we're looking at hybrid or heterogeneous systems where we have CPUs and GPUs interacting, or we're looking at only a homogeneous environment with only CPUs. So we have at this point collected data from different types of configurations, and this is where our expertise lies.
Yeah, and I think to add is the Hacko version is available for free, and like people can just test it out. So that's kind of for developers listening out to use. And like we want to maybe focus the call, and I think this is kind of what becomes interesting around what are the components that are part of Hacko? Like how is this optimization happening in the backend? And this is kind of opening the kimono a bit. Maybe Guna, do you want to run through the pieces? And we're going to do a couple of demos of these things individually so the audience can understand a bit more.
Yep. So, as we can see on the slide, there are 4 major components of Hacko. The first one is the source-to-source optimizer. So this is optimizations which are applied at the source level. So Hacko passes through the input source and gives out a list of recommendations back to the user on what sort of optimizations can be applied at the source level, right? So that is the first component. The next component is the compiler fine-tuner. So we have a long list of compiler flags, right? Often it is very difficult to identify the right combination of compiler flags that we have to use for an application. So what Hacko does is internally it would identify the right combination of compiler flags needed for an application and use those flags to ensure that we get the most performant machine code for that application. Now coming to the next 2 components, we have the intrinsic translation module. Here what we do is if you have a application in x86 which uses intrinsics, we will not be able to run it out of the box on an ARM machine. So we have an intrinsic transformer or translator which would convert the x86 intrinsics into the equivalent ARM intrinsics. So we do have support for SIMD now, which converts all of the AMX, AVX, AVX512 to Neon. We are currently working to enhance this to SVE2 as well. We support complete AES intrinsics now. So all of the crypto instructions and all of the subcategory of the AES intrinsics now can be translated to ARM. And we also have a roadmap where we want to expand the intrinsic support to the other areas as well.
And intrinsics, for those who don't know, are special CPU instructions for doing like more difficult math or like more parallel kinds of math that you might find in things like graphics processing or AI processing, correct?
That's right.
Yep. We have actually an example where we want to share that specifically address kind of the impact it can have on performance, the intrinsics.
Okay. Right.
Awesome. All right.
And
do we want to go right into that, or do you have more slides on here?
Yeah, no, we can go through the example for intrinsics actually. Maybe do you want to, Guna, just to kind of share the example?
Yes. Let me share my screen here. So do let me know when my screen is visible.
Yeah, it's visible. Can you increase your font size there a little bit?
So
Yeah,
cool. Yeah. So I think to showcase the impact of intrinsics that we have seen so far, we've picked up GGML as one of the applications that we want to use in this demo. The reason we picked up GGML is it doesn't have any dependencies, it doesn't have any memory allocation, so it's pretty quick to use for the demo purpose at least. So we'll split the demo into two parts. The first part is where we use existing compilers. So if I look at what my compiler environment variables are set to, I see that I'm using GCC and I'm using G++. So here what I would do is I would just go to the GGML repo, and I've already created a clone of it. So I'm just going to create a build and just quickly, do the build here for you. Let me create a build directory and then so here in GGML, we have picked up two of the inference models that are available. We've picked up GPT-2 and GPT-J. So GPT-2 is one of the inference models which consists of about 7,000 odd books, and GPT-J is more used for text completion or text generation. So here I see that the build is completed, and I'll pick the 6 billion model for benchmarking. So here, while we wait for the benchmark to get downloaded, there are a couple of things I would like to also quickly touch upon here. So we've done a lot of study on GGML, and we've done this sort of study for about 5 to 6 applications across verticals. And the way we have been comparing the data we see is we compare the data with a Graviton, and then Graviton with Hacko, and also compare the performance on a x86 instance and also an AMD instance. So these are the four sort of benchmark points that we have. And one of the key takeaways we'll see shortly in the demo is using Hacko with Graviton performs almost 2x better when compared to the worst scenario here. So the line in orange is Graviton, line in blue is AMD, and the line in green is Graviton with Hacko, and the line in red is x86 instance. So if you see, as we scale the number of CPUs all the way to 16, in each of these cases, we see that Graviton with Hacko has performed considerably better than any of the other instances, right? So let's get back here. Okay, it's still.
And that was with GGML?
Yes, this was with GGML, yes. Right. So a couple of other things that we have done specifically for GGML, and likewise we've created these blogs for two applications, GGML being one of them. So what we have done for GGML is we have done a hotspot analysis, identified the function in GGML which is being called the most number of times and also which consumes the most number of cycles. So in this case, we identified that one of the functions in GGML, vec underscore dot underscore f16, was called close to 99% of the time, right? And we did a further deep dive into this particular function, and we did see that using Hacko actually selected the right intrinsic for ARM architecture. Without Hacko, if you were relying on the traditional compilers to do it, it was picking up an intrinsic which was not the most optimal one. So let me keep a tab on this. Okay, this is still going on. Okay, so while we are downloading the benchmark, we can get into the details of the intrinsic which made a difference. So if we look at the code of the function, which was called the maximum number of times, this is the code of the function. And if you look at it, this is the line here where we are doing computing the sum, which is actually which consumes the most number of cycles within this function. And going into this in a finer detail, we observed that this was a fused multiply add operation, and this internally was calling a half precision intrinsic with eight operands, right? So Hacko could identify that for using a multiply add in a fused manner, we had to pick the intrinsic which had eight half precision uh, intrinsics. But if I use it without Hacko, we were actually falling back to uh, a single precision intrinsic which had only four operands, right? So this is one of the differences that we have seen. Okay, for some reason this download is taking a little more time than I had.
That's okay. We can skip ahead if you want. But quick question: so when it's doing this source code analysis, does it actually provide you the code to say, if it's Intel, use this intrinsics, and if it's ARch64, use this intrinsics?
At the moment, given that we're focused only on ARC, so we sort of scan through the source code, identify if there's an Intel intrinsic residing in the source code, and find the most optimal intrinsic on the ARM side. Okay. So we do not automatically detect if it is using ARM intrinsics, but we rather search for the source files to look if it has any Intel intrinsics. And we cannot obviously run that application with Intel intrinsics on ARM. So we find the equivalent ARM intrinsic, and then we substitute the source code with the ARM intrinsic. Okay. That's what we internally do.
I see. Okay.
So it says that this would take another...
We can continue if not.
Okay. So I think this is one of the examples that we've seen where picking the right intrinsic actually does make a huge impact. So coming to the numbers back again, right? With picking the right intrinsic, we could see in a single threaded environment, we were seeing almost a 2x improvement with Hacko. And likewise, as we kept scaling, the percentage sort of kept dropping, but Hacko always, I think, was the most optimal. It found the most optimal instructions, even as we kept scaling up to 16 threads.
And is this just using that intrinsic substitution, or is it also using the compiler flag optimizations and the source to source optimizations?
So in this particular example that we'll be showing you in the demo, we will only be using the intrinsics, the compiler fine tuner, and the source to source recommendations. We on purpose are not applying the super optimizer here, because super optimizer is exhaustive and it could take at least 3 to 4x of the time a traditional compile would take. So okay. one of the issues that we are currently working on is to reduce the time, the compile time, which a super optimizer takes. So super optimizer, typically it is exhaustive in nature. It looks for all the combinations of instructions and tries to substitute them with the most performant instructions, right? So it's very exhaustive in nature.
Right.
We've seen in cases it takes up to 6x. It increases the compile time by up to 6x. We've seen various numbers. Sometimes it goes up to 4x. But what we're doing at this point is looking out at ways using ML to sort of reduce the compile time with super optimizer.
And it's not something you would have to run every time, right? Like you mentioned earlier, you could just run these, every few commits or every release or something like that, just to make sure that you're getting all those optimizations that you can.
Exactly, right. And that depends on the maturity of the application. I think if application is having lesser changes going in periodically, I think compiling it one time and using it for short duration, I think is okay.
Okay. So what have we got going on your screen right now?
So this is, we are running the GGML application with GCC at this point, and we're using the 6 billion model at this point. So it is printing out, so this again, the GPT-J model, it does text completion and text generation. So based on an input seed, it is identified that, the vocabulary, the number of, so these all are called the hyper parameters for the model. And here it's going to be printing out about 50,000 words at this point, right? So okay. We'll try to use the same benchmark when we run it with Hacko. And so here, if you look at it, to run GGML with the traditional compilers, it's taken 297 milliseconds per token. Right now, we would like to repeat the same exercise with Hacko. So all we need to do for running with Hacko is that we have to configure the compiler environment variables. So I'll come back to this in a minute when we start off the build process. So all we have to do when we are wanting to run with Hacko is we have to configure the environment variable CC, C flags, CXX, and CXX flags. In this particular case, we are building this application again. And as you can see, we have configured the C flags in such a way that we only have the intrinsics on and the source-to-source compiler on. We've turned off the super optimizer at this point for the demo. But offline, I think we would also recommend that we use a super optimizer for the demo. We have to go through the same process of downloading the model again.
We should have kept a copy of that.
The thing is, I wanted to get a new start at the build directory to show that we're not saving off any cache data or something like that. So that's the reason we are doing the whole download again.
Okay. So while we wait for that download, I've got some questions about how Hacko works. So you're showing the examples with a C library, right?
Yes. Mm-hmm.
What languages can you use Hacko with currently?
Right. So at the moment, we support C and C++. Okay. And we have done a lot of study to understand what is needed to have a language like Python or JavaScript supported as well. And I think we've done the initial study to understand what is needed to get it done. Mm-hmm. And we have all of this in the roadmap. Again, it's going to be based on the customer need at this point. Like what exactly are the customers looking for?
Right.
Those would automatically drive the priority of what language we pick next.
Okay.
But I think maybe to add up that we can easily support Fortran, because as we are LLVM based, I think it's the natural way to go. And I think then the next step is to support Rust, and maybe we will be able to support Go. I think this is in the roadmap.
I was going to ask about those other compiled languages because for me, does make more sense. Is it for Python or for JavaScript? You optimize the runtime, but not individual applications for the most part, I would imagine.
Actually, that's what we are doing now in our experiments. We are working with PyTorch and TensorFlow, and we are running Hacko to optimize these runtimes and trying to see if we have some benefits. We have seen some 5% benefit in TensorFlow, and there's about also to confirm the benefits for PyTorch, but this is an ongoing work, so we will be reporting it soon, hopefully.
Okay. And what versions of ARM do you support? And which intrinsics, I should maybe also ask?
There's a lot. I mean, yeah. The list is pretty exhaustive. We have grouped them together, right? So we have done a big work with one of a university just to group them and kind of figure out, since some of them are, we can support some and that encompasses others, right? So we've done a pretty good work. I mean, the list is like in the hundreds. I would like to rely on Guna on this one.
Yes. I think it's a big list, especially on the intrinsic side. And if you want to break it down, right, SIMD itself has multiple set of instructions. So we are creating templates for, we are grouping the instructions together, and based on the operand changes, based on the source and the destination and things like that, we are creating groups. And I think that's what we will be using for the intrinsic translator. But we cover SIMD now at this point, and we also cover all of AES. So these were, I think, in the priority we created, these were the instructions which were most often used, and that is what we have.
Okay.
In fact, I think there's one of the slide which talks about NumPy and SciPy. I think just using what Hacko supports at this point, uh, they have seen like almost 200x improvement on ARM architecture just by using the SIMD intrinsic.
Yeah. So I think intrinsics are a big thing that are completely overlooked, like just because people don't know that they can apply them. And there's this like, if for AI companies watching, like, vector databases are a big deal that are running on CPU. And like these two libraries, for example, and I have just by implementing a couple of intrinsics, they either from AVX or like the different types, they've seen like between, I think it's 3x to 300x depending on the library. So it's a good reminder that intrinsics can really help, especially for those AI companies.
So you mentioned earlier that Hecko is still in beta, right? Can open source projects start using this, and can they use it for free? Maybe I should add to that because I know that's important to a lot. But can projects like TensorFlow or PyTorch start using Hecko now to improve their code base and how it runs on ARM?
Yes, 100%. I think that's the whole intent, is to kind of upstream. We are actually, Raul, he's doing, maybe Raul, do you want to just kind of maybe talk through some of the stuff you're doing for LLVM, upstreaming it?
Yes.
Sure, maybe I can share my screen while we finish downloading.
Yeah, we can do that.
So let me just go through it.
And just a reminder to everybody watching our video live, you can ask questions in the YouTube chat, and we will see them here, and I will ask them of the appropriate guest.
Can you see my screen?
Yes.
Yeah, cool. So one of the parts that we are working at the product is to provide optimizations at the source level before the compilation, like what we call the static code analysis. So one of the opportunities we saw is that there are plenty of code bases there that haven't been parallelized, for example. And one requirement for parallelizing these loops, it's like they have to be in a certain form. Like, for example, here in the line 15, we see that there is a loop that doesn't contain any init part. Or, for example, there's another loop here in line 42 that misses the init part and the conditional. So we have created a tool that detects these cases, and it's like in the form of a compiler that it emits warnings in this case, and we can see that we can detect those cases. Like, for example, line 15 is telling us that we are missing this init section, but it's also pointing at us where can we find this initialization part. So it's telling us that we can go to line 8 and find that initialization. So the programmer should go and fix the code itself in this case. But in the future, what we want to do is to make this transformation automatically, so that in line 15, we insert automatically this missing part. We also have a case that we detect when a break statement is written inside the loop. So like in line 15, and we are detecting where is this break located, because for parallelizing these break statements can make it difficult. The next step that we want to target is to insert the OpenMP directives for parallelization in an automatic way. Like, for example, that the IDE is able to do this. Detect that this is a loop that can be parallelized. So that's in the roadmap of this tool, and we are planning to upstream these collaborations into LLVM. We want to put it into the category of the Clang extra tools, where you can do static code analysis, and we are working on that to have these open for the community.
Okay, and this doesn't change the meaning of the C code. It just means that you can use these optimizations that you couldn't before because of the way it was written, not necessarily because of what it was doing.
We have to try to keep the semantics of the program, of course, but I think there has to be also a consideration from the programmer that these semantics don't break, because it's not only about adding the directive. it's also you have to make sure that you solve some data races conditions or that you apply the atomics when they are needed. No, so we see this tool like a recommendation tool that performs automatic changes in your code, but at the end, you as a programmer have to make sure that the semantics are kept. Yeah.
Right. All right. Do we have that download finished, Gunnar?
Yes, we do have it. Yeah. So let me share my screen again. So we do have the data from Hacko as well now. And the compilers you see here, right? We are using Hacko for CC and then Hacko++ for CXX. I would like to quickly show the output from GCC and from Hacko. So I think what I would like to focus is like the seeds are different here in both these cases. But if you look at the parameters passed to the model, they're exactly the same, right? And the key takeaway here is without Hacko, it took 297 milliseconds per token. And with Hacko, it took 126 milliseconds per token. So here we have four threads enabled. Yes, it's almost twice as fast. And this is with the 4 threads enabled. And we have done the experiment, like the graph I had shown earlier was actually scaling up all the way up to 16 threads.
And this didn't require a change in the project code, right? This was just using Hacko as the compiler?
Yes, yes.
Very cool.
Yeah, I think we can share, Michael, some examples of where we're seeing this used, if that's okay, like some kind of, hey, libraries. There's
I wanted to ask you what your favorite success story was. So yeah, let's do that.
Awesome. So yeah, I think this was the example that I was referencing, like, and this is not our work. It's just Ash, like a person has done it and make it open source, but I think it proves the point around how faster things can go with intrinsics. And like, because people don't know the details of this intrinsics, just using Hacko as a front end can really make it faster. And this requires work from everybody, right? Like, I think we have here some use cases, like, cloud vendors making libraries faster for their customers, or even like cloud native companies. We've seen a lot of the work relies on like the performance engineering team or the platform team to optimize libraries for the full company. And this can mean, maybe they just look at like the hotspots, but most of them have not even considered intrinsics or have not even considered parallelization part. So that is another good example. And for AI companies or even like hardware companies, like they were seeing some want to use it as a differentiator. Like, hey, I'm relying on this open source library, but I want it really, really optimized for my business so it can be much faster or much cheaper. So that is another, maybe for storage or different scenarios we're seeing being used today.
All right. So we had a question from my colleague Gabe, who's doing production for the show, and he is asking, with cloud providers offering their own optimized solutions for ARM-based CPUs, such as Graviton, how does Hacko differentiate itself and maintain a competitive edge over them?
So, as you mean from a hardware standpoint, or from a library, like? Can you maybe...
Or say if you're a developer, why use Hacko instead of using something that's maybe provided by AWS?
Yeah, and I think like we want to build over, and we are building over in conjunction with AWS, or like it's not, I think, either or. Like there's a lot of like great optimized libraries from Ampere or from AWS, and we're using Hacko over those, like, or even like open source. Like, so I think we are working together with like the ARM ecosystem, and our intent is to kind of build over for the sake of developers, not be either or scenario. I think we build over the latest version or the most optimized version that's out there.
Okay.
Does the team want to add something on that, or?
Yeah. I think just to add one point here, what Hacko does at this point over existing compilers is it finds the optimizations automatically. We do not need to preset them or configure a rule for a particular optimization. Automatically, these optimizations, I think, based on the instruction stream, these optimizations are automatically decoded and then they're applied by default by Hako. So it's over the existing solutions which we have. It's working together with them as well.
Okay.
Cool. So I think just to close, like, I think there's a great of examples out there of companies that are already doing optimizations, and like now as new optimizations are uncovered or SVE or some other good stuff, like we're working with some of them to kind of keep increasing their margin or reducing their unit cost. So those are all kind of good things that are happening, and for all those ARM users, it's a really good opportunity to look at these things. And I think we have some examples here of like generic applications, like the improvements we can get and like the things we are applying, like from the modules you guys have seen. And there's more in the webpage, just like examples of, normal applications that already have great improvement with ARM and then have even better improvement when we apply Hako on kind of the different things that it includes.
Nice. And have you seen any of these optimizations being incorporated back into these upstream projects?
We're right there right now. Like we're working on those things right now.
Nice. So if somebody has an open source library that they want to optimize for ARM, how can they get started using it?
Yeah, so in our webpage, it's just downloading Hako and replacing it as the front end of the compiler, as Guna has shown today, and just also giving us feedback like, hey, I need this, or kind of providing us feedback on the language part, especially. That is kind of our next step as a company to expand it to. But I would just say, just test it out. We've seen tests coming up from hotspots, like only a certain part of the library that is, easier maybe than the full library, or depending on the customer.
Okay. And if I remember right, you have Debian packages that people can just download and install on a Linux system?
Yep, that's correct. We have a Debian package that is for free and available today from our webpage that people can start using.
Excellent. And how can people get you that feedback?
So we have an email actually that we are receiving quite a bit of feedback. And also, I think there's on the repo, I can't remember now if there's commits coming up from different customers. So yeah, I think most of it today. And we also have in the Cloud Native Foundation, we have a channel that is specialized for Hako, and we have people providing feedback there too, or examples.
Okay. One last question from me. I've personally been doing a lot of stuff with embedded devices, things that use like Cortex-M processors and the thumb instruction set. Does Hako cover any of that, or do you have plans to cover any of that?
Well, I'll leave that one to Guna. He's prioritizing all the things we get.
At the moment, we do not support thumb or Cortex-M. But again, if you have a use case and you think that that's an area where we can make an impact, I think we are open to have a discussion and understand what needs to be done.
Sounds good. All right. And of course, if anybody is using this, I would love to hear your stories to see how much more speed or performance you can get out of your code. So if you use it, join our Discord. It's the ARM Software Dev Discord. Gabe, can we put the link up to that? Yeah, so join that and talk to us there. And I hope the three of you also join our Discord there and can talk directly to some of our ARM software developers and help them get started using Hako, because this is a really cool technology. And I love the fact that you don't have to know all of the intrinsics. You don't have to go through your own code line by line to figure out where and how to apply those. You just start using this compiler and it starts giving you all this stuff for free. And I'm always for free optimizations.
Awesome. Yep. So are we. And this is definitely where we want to go, like helping the open source community. And also like on the closed source, we're doing some individual projects, but I think it's all about helping expanding the ARM ecosystem. So excited to help.
Yeah. And where do you see the business going now from here? You've got the beta out. What's your timeline for that becoming like a GA release, and what's your business plan afterwards?
Yeah, so we are definitely thinking of how we can like expanding the team and prioritizing the information, like all the requests that we get. From a language standpoint, I think the language is one of our kind of in it. And then also like if there's other architectures or increasing the number of benchmarks, I think that's a big one for us. Like we get a lot of requests like on different applications. So I think those our priorities are there. Maybe Guna, I don't know if you want to share. He's responsible for the product, so maybe there's more there.
So I think Micah covered the complete. So we're getting a lot of requests, and at this point, we're just trying to sort of prioritize what is needed based on the feedback that we are getting. So yeah, I think more feedback is welcome, and we are actually looking into almost how we can get better always. We're constantly evolving as well, so I think more feedback is always good.
More feedback is always good. And one last question I had, you mentioned something earlier about using ML to try and make Heko better. And obviously you're focusing a lot on AI and ML libraries because there's a lot of ways to improve the performance of those using intrinsics. Does it currently use any ML or AI? And if so, what did you use to train that?
So at this point, we are still so we are using a cache and a database internally, and we use ML to a smaller extent now in the beta version. But we are currently working on a prototype which will create more vectors and improve the compilation time predominantly. So what happens is at this point, given that the super optimizer is exhaustive in nature, many times we will hit a timeout for not finding the most optimal instruction, and we would drop those instructions and move on to the next set of instructions. So what we're doing at this point is to create a database or create a cache. We're working on the prototype now, where automatically, if in the past we found a mapping, we would want to leverage from that, right? So it could be either based on the number of source operands, based on the number of destination operands, based on the register set which is being used, right? So we are trying to save off all this information to identify if a particular mapping was found in the past and directly reuse that, instead of rather than going through this whole search every time. And one other thing we're trying to do at this point is the search, the slice criteria at this point is limited to 5 instructions in the super optimizer. We want to sort of expand it beyond 10 to 12 instructions, which could compromise of a full function in that case, right? So that way we can just pass a whole function and the whole function can get optimized at one go. At this point, we have a limitation on the number of instructions we can pick at a time. There's a limitation on the slice extractor, at least at this point. So these are two of the things where we are applying ML, where we intend to apply ML in the future. And this will definitely be part of the next release that we'll be making.
Cool. All right. So I think we've covered everything. Is there any last minute things that you want to plug or something that you want to encourage people watching this to go and do?
I think just for people watching is to go to our webpage, either download the executable Debian package or to use the online version, like just for a hotspot that you can just input code, as you can see in the screen, and just kind of get the optimized version. You can test different things on it. So I would just say use it and give us feedback. And we're still a startup, but we're definitely wanting to help the community and get that feedback to prioritize the pipeline of activities we're going through.
Fantastic. Guna, Rob, do you either of you have something you want to plug?
Oh no, I think at this point, I think Micah has covered everything. Yeah.
All right. Well, I want to thank everybody for watching. I want to thank the 3 of you for being our guests. I know this was kind of short notice for you. We just talked yesterday to get you on. So thank you so much for joining us on short notice. This has been a really fascinating innovation coffee. I really appreciate that. Once again, if you like this episode and you want to see more of these, hit that like button, subscribe to the ARM Software Dev YouTube channel, and join our Discord. We post updates every time we do a broadcast in there as well.
Awesome.
All right.
Thank you.
Thank you, everyone.
Thank you. Bye-bye.
Bye-bye.
Thank you.